Just a couple announcements before we get started. This week is going to be a bit of a weird week because we are actually almost done with the content for this unit. Like I talked about a little bit last week, the stuff in this unit's a little bit trickier, so there's a lot less of it so we can get extra time to practice. So class today is actually going to be very short. There's I think 3 slides on examples from stuff from half angle identities. If you remember, we did something called double angle identities on Thursday. So we are going to do half angle identities today, which are very similar, but honestly, some of the trickiest identities to work with in this unit. And then tomorrow, we are going to have a practice day. So my plan is just to get together a bunch of proofs and do a bunch of proofs during class. I am open to other things as well. If anyone would like to do any certain examples of something, for example, if you're working through the ALEKS maybe or the homework and you're like, hey, I'm having a hard time solving equations with Pythagorean identities, shoot me an email. We can do some examples of stuff like that. Pretty much anything you want to see an example of, just shoot me an email and we can do an example in class tomorrow. I have not written the lecture for that yet. So just anything you want to do, let me know by the end of the day today and I will make it work. So your exam is this Friday. So today is going to be a short class. We're going to just wrap up half angle identities and then we'll be done with new content for the unit. Tomorrow will just be practice with proofs primarily, maybe a couple examples of equations if anybody wants. And then Wednesday is going to be your review for the exam. I will put out that review, if not tonight, by tomorrow morning. And that will be just like what we did with last unit. It'll be a little worksheet type thing with a bunch of different examples from the unit that I will go through during class. ALEKS is also a great tool to use for a review if those are not enough. And then Thursday, I have a conference to go to, so we will not have class on Thursday, but I will respond to emails as they come in. And then Friday, there will also be no class because you will be taking the exam. And that will work just like last time. You'll have that entire 24-hour window to take the exam. It'll be 90 minutes within that time frame, but you'll have the entire 24 hours. So that's what this week is going to look like. Any questions on that? Okay. Speaking of exams, I have all of your exam ones graded. I actually had them graded a while ago and I learned, some of you informed me that your comments did not go through on Canvas when looking at the old exams. So those are now uploaded as a file as like a comment in the form of a file to the assignment. So if you go back and look at my submission comments, you should be able to download and see all of the feedback. If you have any questions on that or want to go over anything from your exam, let me know. I have office hours Tuesday this week because I will not be here Thursday, and Wednesday like normal. So whenever you want to go over those or just any other time, shoot me an email and we can work something out. Yeah, and I will have your next homework out shortly after class. Questions on anything logistics-wise? All right, then we only have a little bit of content to cover today, so let's go ahead and get started. I will share the slides. Here we go. Okay, so if we remember last time, one of the main focuses of what we did in class was these double angle identities. And that's where if we had an angle that maybe was 2 theta in a proof or something, we could get rid of the 2 inside of the argument by replacing it with something like this. For some reason, the one for cosine had 3 forms, and that was just using Pythagorean identity to simplify it down into different ways. But we practiced using these 3 formulas to do proofs or to find solutions to equations like this in order to eliminate the 2x in the argument there. Now we may see another kind of these, and that's called the half angle identities. There's also one for sine, cosine, and tangent. And essentially what this is say we're given an angle that we don't know, but maybe if we double it, we are going to be familiar with it. So that would be what the half angle identities are used for. You'll see an example of that in a second if that didn't make sense. But notice instead for this one, there was 3 for cosine, and we showed why there were. We could just use Pythagorean identities to get from this one to this one to this one. In this case, tangent has three identities. It has this form, and this form. I will explain and prove a little bit why that works in a little bit, but just know for tangent, we have three forms for this one. And notice that there's a plus or minus in front of all three of these. I will explain how to determine that when we do an example. So let's do an example. I want to use a half angle formula to find the exact value of cosine of 5 pi over 8. Now, again, we could plug cosine of 5 pi over 8 into our calculators in radian mode because that would give us a value. However, it would not be the exact value. It would not be a radical. It would be some kind of decimal. And whenever we see the words exact value, I want something with square roots in it typically, or pi, something that looks like maybe square root of 2 pi over 3 or something. That's not the answer, but when I say exact value, don't want square roots evaluated, want pi's left alone. So how do I do this? Well, cos 5 pi over 8 is not an angle on my unit circle. We don't work with 8s on the unit circle. It's not one of the familiar friendly radian values that we're familiar with. However, what if I notice that 5 pi over 8 times 2 is equal to 5 pi fourths? This is a familiar angle on our unit circle. I could work with 5 pi fourths. I can't work with 5 pi eighths, but I could work with 5 pi fourths. I could work with 5 pi eighths times 2. So is there a formula I have that I could use for this? Well, let me just write down, I have this half angle identity, and it says to use a half angle identity, and I know I want the cosine of something, so let me just write this top one down on my next slide. I know that the cosine of theta over 2 is equal to plus or minus the square root of 1 plus the cosine of theta over 2. Okay, what do I do with this? Well, if I set theta to be 5 pi eighths, I can't really do anything because then the 5 pi eighths would be in here. I don't know how to find that. And then I find out here, I get 5 pi 16ths, which is not what I want. However, what if I say, let's set theta to be equal to 5 pi fourths? Then I would know that the cosine of 5 pi fourths divided by 2 is equal to plus or minus the square root 1 plus cosine 5 pi fourths over 2. I know I can find this value here, and then it would give me this value here. And what's this value here? What's 5 pi fourths divided by 2? Well, that's just 5 pi eighths, and that's what we want is the cosine of 5 pi eighths. So we can use the half angle formula because we know what double, we could find the cosine of double 5 pi eighths. We can't find the cosine of 5 pi eighths, but if we could find the cosine of just 5 pi fourths, which we put in here, and we set theta to be 5 pi fourths, it would give us the cosine of 5 pi eighths. Cool. So let's evaluate this guy right here. What's the cosine of 5 pi fourths? Well, using my little fancy unit circle, I can draw a picture. I know that 5 pi fourths is right here because I go 1, 2, 3, 4, 5 pi fourths around the unit circle. And if I remember my unit circle values, I know that that is negative root 2 over 2, negative root 2 over 2. That is where it intersects the unit circle. And I know my cosine is where that ray intersects on the unit circle, the x value. So the cosine of 5 pi fourths is negative square root of 2 over 2. Plugging that in, we get that the cosine of 5 pi eighths using our half angle formula is equal to plus or minus the square root of 1 plus a negative root 2 over 2 over 2. Simplifying that numerator down, we get that it's plus or minus the square root of 2 minus square root of 2, just turning that 1 into a 2 over 2, over 2, and then over 2 again, which is equal to plus or minus, I'm just doing arithmetic here, 2 minus square root of 2 over 4, and then taking the square root of the numerator and the denominator, it's plus or minus the square root of 2 minus square root of 2 over square root of 4 is just 2, so the square root in the denominator goes away. Cool. we almost have our answer. It's going to be this number here because that is as simplified as I can make it. However, what do we do with that plus or minus? Well, the plus or minus is determined by the quadrant with which theta over 2 terminates. So let me explain that. We know, for example, if I just asked, okay, give me the sine, like, is the cosine of 3 pi fourths positive or negative? It's that kind of question. So let me redraw this diagram that I draw a lot to solve certain problems. So what does this diagram tell us? Well, this diagram tells us is if we have an angle that terminates in quadrant 1 over here, that it's going to have a positive cosine and a positive sine. If it terminates in quadrant 2, we're going to have a negative cosine and a positive sine. If it terminates in quadrant 3, we're going to have a negative cosine and a negative sine. And if it terminates in quadrant 4, we're going to have a positive cosine and a negative sine. So we want to determine which quadrant 5 pi over 8 terminates in, because that will determine the sine of its cosine. Notice I don't care about 5 pi fourths. I don't care about where 5 pi fourths terminates. It doesn't matter. We're not trying to find the cosine of 5 pi fourths. Because we are looking for the cosine of 5 pi eighths, I want to know which quadrant 5 pi eighths terminates in to determine whether it has a positive or negative x coordinate to determine the sine, the positive or negative sine of the cosine. So if you remember, this angle right here is pi over 2. This angle right here is pi, 3 pi over 2, and then that's 0. Sure. 5 pi over 8 is a little more than 4 pi over 8. 4 pi over 8 is another fancy way to say pi over 2. However, 5 pi over 8 is not quite pi. So we know that 5 pi 8 terminates somewhere over here, i.e. it terminates in quadrant 2. If we look, it has a negative x coordinate, therefore the cosine is negative. So our final answer here is that the cosine 5 pi 8 is equal to negative square root of 2 minus square root of 2 over 2. Because we are looking at a negative cosine because we terminate in a quadrant where the x coordinate is negative. Questions on this one? Purpose of these is just to get comfortable with recognizing, okay, I don't know 5 pi 8, but is there something I could use a formula? In this case, you would probably look to either the double or half angle identities. That should be where your gut tells you to check. Is there something I could use to evaluate this? And a half angle identity works. You just have to be careful. Just because 5 pi over 8 is what we're trying to find, we do not set theta equal to 5 pi 8. We set it equal to double theta, so we are able to use the half angle formula. Okay. Well, if there's no questions on this one, let's try to solve an equation using these. I want to find all solutions to the equation 1 minus cosine squared x equals 2 sine squared of x over 2. Previously, my gut instinct for this would have been, okay, we have a cosine squared and we have a sine squared. Neither of those are what we want. So in the past, almost every single time when we've seen something happen like this, we've wanted to use a Pythagorean identity, because I know I could make that cosine squared a sine squared minus 1, or a 1 minus sine squared. I know I could get rid of the cosine squared that way. However, I have this pesky x over 2 here. I don't like that. I can't work with something in my argument like that. So let's see what happens if we attack it with a half angle identity to get rid of that x over 2, and then see if we can work with what we have. So if you remember from the half angle identity sheet, the sine of theta over 2 is plus or minus 1 minus cosine theta over 2. So I'm just going to write that down in the upper corner here, just as a reminder. The square root of 1 minus cosine theta over 2. Okay, so before I try to attack this with any Pythagorean identities or get rid of stuff that way, I'm just going to try to work with this and see if it helps us at all. So we have that 2 sine squared of x over 2. I'm just going to rewrite this before I use the half angle identity, just to remember how this is supposed to work. Remember that it's 2 times the sine of x over 2, all squared. That squared does not affect the x over 2. That's not how that works. Remember, once we take the sine of x over 2, we're squaring it. So hopefully rewriting it like that. And then now using the half angle identity, we can see that we have 2 times, we want the sine of x over 2. So that's plus or minus the square root of 1 minus cosine x all over 2. And then that quantity is squared. Okay, this looks messier. This looks like I made it worse, but I promise I didn't, because here's something really nice. We have a square root here that is being squared, and those two cancel each other out. But before I do that, I want to take a really quick mental check to think, okay, I have this plus or minus in front. What happens to that plus or minus? Well, it actually goes away, and you can intuitively check why. For example, let's know that 2 squared, for example, is 4, but negative 2 squared is also 4, because negative times a negative is a positive. So regardless of whether there's a negative or a positive out front here, that negative will always go away. The answer will always be positive. So when we square this, moral of that story is that this plus or minus will actually just go away. It completely eliminates the need for us to even consider it, because when we square a number like that, the plus or minus just completely goes away. So what this is going to end up being is just 2 times 1 minus cosine of x over 2. The squared and the square root cancel each other out beautifully. And then these 2's cancel each other out, and we're just left with 1 minus cosine x. That worked out really nicely. This looked so ugly, but just by trying our half angle identity, we got it down to this. So what does that mean our equation looks like right now? Just writing it out, we have 1 minus cosine squared x, just the left-hand side, is equal to our new right-hand side is 1 minus cosine x. This looks a lot more familiar and like stuff we've dealt with before. So let's simplify it, see what we can get. I'm going to add a cosine squared x, add that over to the right-hand side. So we have 1 equals cosine squared x minus cosine x plus 1. And then subtracting a 1 from both sides, I get that cosine squared of x minus cosine x is equal to 0. Cool. This is really easy to solve. We don't even need to think about doing the AC method of factoring or anything, because we can already just pull a cosine x out of everything. So just factoring a cosine x out of both terms, because they have a cosine x in common, you can see that cosine x times cosine x minus 1 is equal to 0. It's now in factored form, and we're to the point where we can set this factor and this factor equal to 0 and see what our solutions are. So I get that the cosine of x is equal to 0. So what angles on the unit circle have an x coordinate of 0? Well, drawing it out. Oh, that was an oval. There we go. We want to know which angles have an x coordinate of 0. Notice on the unit circle, x is 0 right here and right here. These angles are pi over 2 and 3 pi over 2. Cool. It wants all solutions, so we'll write these in the general form in a second. But first, let's just solve cosine of x minus 1 is equal to 0. Solve the other factor for when it's equal to 0. So we want to know when the cosine of x is equal to 1. In other words, what angles on the unit circle have an x coordinate, because cosine of 1? Well, on the unit circle, x is 1 precisely right there and nowhere else. What angle is that? Well, in the principal interval, that's just x is 0. Cool. So how do we write these in general form? Well, for x is pi over 2 and 3 pi over 2, notice that we walk around pi radians, and then pi radians again, and then pi radians, pi radians, pi radians. They're all pi radians apart. So we don't need to write these as two separate equations. We can keep them together. So we can just write that x is equal to pi over 2 plus pi k. We don't need to do the 2 pi over k thing, because we can just nicely jump from solution to solution in increments of pi. Also, we have the x is 0 as one of the solutions. And that's the only solution. We need to go around in intervals of 2 pi to get from solution to solution. So we write that this solution in general as just 2 pi k. because it's 0 plus 2 pi k, but we don't need to put the 0 in there because why would we add 0 to things? And just remember, we have to write that k is in the integers. And those are your solutions. Questions here. If you ever see anything like a 2x or an x over 2 when you're asked to find solutions to an equation, always, 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 I would say 99.999% of the time, it's going to be a double or half angle identity. Probably 100% of the time in this class, quite honestly, I can't see any reason why there wouldn't be. So just try hitting it with one of those two identities, the one that makes sense for the context you're in. And then if things don't work out, maybe use Pythagorean identity then, but most of the time, just using the half angle identity or the double angle identity will make it simplified nicely. Okay. So remember how I said that there were two different half angle formulas for tangent, or three different ones actually. The first one, pretty easily we can see, comes from just dividing the half angle formula for cosine by the half angle formula for sine, because the half angle formula for cosine was just 1 minus cosine u over 2, and the half angle formula for sine was just 1 plus cosine u over 2. So just dividing those two gave us that one. But where did these other two come from? The sine u over 1 plus cosine u and the 1 minus cosine u over sine u. This is just a little bit of an interesting thing to see where it came from. You're not going to need to know this, but just in case you wanted to see, this is where they come from. So to get the first one, sine u over 1 plus cosine u, I took the half angle formula that I got up here. That's all that is. And then I decided to multiply it by the conjugate of the numerator. And remember, the conjugate is just if I have a plus b, its conjugate is just a minus b. That is all I mean when I say the word conjugate. I just take the second term and switch the plus sign to a minus sign, or vice versa, minus sign to a plus sign. And again, it may not seem immediately evident why that works, but we'll see once we do this third step, multiplying by the conjugate of the numerator. So if I want to take 1 minus square root of 1 minus cosine u times the square root of 1 plus cosine u, I just get the square root of 1 minus cosine squared u. In the denominator, if I multiply 1 plus cosine u, the square root of 1 plus cosine u, times the square root of 1 plus cosine u, it's multiplying a square root of something by its square root, which by definition just gives us the thing back. Cool. The denominator already looks like what we want it to. However, the numerator almost does, but not quite. Remember, by the Pythagorean identity, that the sine squared of u is equal to 1 minus cosine squared of u. So we could replace the thing under that square root with a square root of sine squared u, and then just taking the square root, the squared goes away and we're left with sine u. So that's where that top one came from. Similarly, the bottom one is pretty much came from exactly the same place, but instead of multiplying by the conjugate of the numerator, we multiplied by the conjugate of the denominator. So in the numerator, that means 1 minus cosine u times square root of 1 minus cosine u, the square root run away, and we're just left with 1 minus cosine of u. And then in the denominator, we are just left with the square root of 1 minus cosine squared u, which for the same reason works out to be sine u. You're not going to have to know this, but sometimes I know for a lot of people, it's nice to see where things come from, because this feels like it was pulled out of the blue, and how the heck is it equal to this? It is, you're not going to need to know why, but just in case you do, this is nice to look at if you're that kind of understander, but you're not going to need to know that. Just a little sidebar. Okay, so we have one more example to do today, and that is using these tangent identities that I've just written up here as a little bit of a reminder. So suppose I have an angle whose tangent is negative 15 over 8, and we know that this angle is between pi over 2 and pi. In other words, it's in the second quadrant. I want to find the exact values of sine of theta over 2 and tangent of theta over 2. Now, this is one of the, I would argue, is one of the trickiest kinds of problems we have in this class, pretty much for the entire semester. And the reason for that is it's a lot of information to try to pull apart and figure out what we're supposed to do here. So let's try to work with what we have. I know that this is the tangent of my angle and it is in the second quadrant. Let me draw that. Drawing a picture is always, always, always a good idea. So I'm going to draw that picture. Here's my theta. It's in the second quadrant, or my alpha. If we recall from very early on in the semester, I know that the tangent of alpha is equal to the y coordinate over the x coordinate. So I know I have a y coordinate of 15 and an x coordinate of 8, but it's a negative 15 over 8, and we're in the second quadrant, so the x values are negative, so this is actually a negative 8. I want to find the sine of alpha and the tangent of alpha. I don't really know how I'm going to do that yet, but I know I'm probably going to need the sine of alpha to get the sine of alpha over 2, and maybe the cosine of alpha to get the tangent of alpha over 2, seeing as there's a cosine in every single one of these equations up here. So I'm going to solve for the hypotenuse of this triangle because I think I'm going to need it. So to do that, we use Pythagorean theorem. Negative 8 squared plus 15 squared is equal to, I'll just call that r for now, r squared. 64 plus 225, I believe, is equal to r squared, which means that r squared is equal to 289, and the square root of 289 is 17. Since we're working with a radius, we know it's going to be positive 17. So I will write that in. Cool. We have our triangle completed. Nice. Okay. Now, if I recall from the half angle identities for sine, yep, right here, I'm going to need the cosine of theta for that to get the sine of theta over 2. And for tangent, I'm going to use one of these formulas over here because they're much nicer. I don't have to think about plus or minus. So I'm going to need the sine of theta as well. So the sine of alpha is equal to y over r, if we remember from the beginning of the semester, which is the y coordinate is 15 and the radius is 17. And the cosine of alpha is equal to x over the radius, which is equal to negative 8 over 17. Okay, we now have the sine of alpha, the cosine of alpha, and the tangent of alpha all easily at hand. I think we can work with these to solve our equation. So what's the half angle formula for sine of alpha over 2? I'm just going to write it out in general terms first from our little cheat sheet up here. The sine of alpha over 2 is plus or minus the square root of 1 minus cosine alpha over 2. I'm going to write that down. Okay. So we know what cosine alpha is. We have the tools we need to solve this. So that's equal to plus or minus the square root of 1 minus the cosine of alpha over 2 is negative 8 over 17 over 2. Minus a negative 8 over 17 is plus 8 over 17. So we get plus or minus 1, or we have 25 over 17 because 17 over 17 plus 8 over 17 is 25 over 17 divided by 2. Simplifying that out just into one fraction, we get that it's a square root of 25 over 34. And then taking the square root of the numerator and denominator, we get that it is 5 over square root 34. But I want to rationalize my denominator because in math, we don't like square roots in our denominator. So that is 5, or plus or minus 5 times the square root of 34 over 34. Okay, now I have to think about that pesky plus or minus, except the thing is here, we don't know what alpha over 2 is. Remember, the plus or minus is determined by the sign of the y coordinate of alpha over 2. But we only know where alpha is. We know that alpha is in the second quadrant. We don't know anything about alpha over 2. We can actually get that information really easily. If we notice in this equality, we have pi over 2, alpha, pi. What happens if we divide all three sides of this inequality by 2? We get that pi over 4 is our lower bound. Hey, now we're working with alpha over 2. So we know that alpha over 2 is actually between pi fourths and pi halves, which if we draw that out, Here's pi fourths, here's pi halves. So we know that while alpha is in this little guy over here from pi over 2 to pi, we know that alpha over 2 is in this little sliver here. Where is that little sliver? It is entirely in the first quadrant. So we know that the y value of alpha over 2 is positive. Therefore, the sine of alpha over 2 is going to be positive. So we're working with a positive 5 square root 34 over 34. And that is our final answer for sine. Questions on that deduction? I don't care what quadrant alpha is in because alpha is not the concern of the sine or the tangent. We're not looking for where the sine of it, where alpha is or where tangent of alpha would be. We're looking at alpha over 2 because that is the angle we're evaluating the sine and the tangent of. So we don't care where alpha is. We need to figure out where the angle in this argument is. Okay. Let's do tangent really quickly. And I don't want to deal with this plus or minus shenanigans again. That was a lot to think about. So I'm going to use one of the two formulas that doesn't deal with the plus or minus. I'll just pick this at the end. Hi, someone have a question? No. Okay, maybe I'm hearing things. Okay, I'm just going to pick the one on the end because it doesn't have a plus or minus, because when we derived those formulas, the plus or minus nicely went away. So I'm just going to use this formula on the end here to calculate the tangent of alpha over 2. So tangent of alpha over 2 is equal to 1 minus the cosine of alpha over sine of alpha, which is equal to 1 minus our cosine of alpha is a negative 8 over 17 over the sine of alpha, which is 15 over 17. So simplifying that numerator, I get that we are working with 25 over 17 over 15 over 17. The two 17s and the denominators cancel. We're left with 25 over 15, which simplifies to 5/3. The tangent formulas are much nicer to work with because you aren't dealing with square roots, you aren't dealing with plus or minuses. There's no way to get rid of the square roots in the sine and cosine formulas, which is why we only have one form of those. But when we're working with tangent, we can really nicely just get answers like this and not have to deal with thinking about pluses or minuses. Questions on this? Questions on the half angle identities at all? Okay, well, yep, it's 11:10. That's about what I thought. This is all of the content for this unit. So you should be able to complete every ALEX module up through this unit. You have all the tools. It's going to be really, really handy to have your course packet on hand. If you've seen it, you should have seen it already. One of the reference pages in the front has the list of all these identities we've used: Pythagorean identities, reciprocal identities, double half angle identities, all of them, co-function identities. Those will all be incredibly useful to have on hand when you're doing the ALEX. And even for the exam, I personally have very, very few of them memorized. I have the Pythagorean identity memorized, and that's pretty much it. So you are allowed to have a note card for the exams. I would highly, 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 highly recommend putting these identities on that, because you don't really need to memorize them. You just need to know how to use them. But yeah, so you should be able to do all the ALEX. I will put out another homework tonight. It will be due Thursday instead of Friday because the exam is on Friday, so it won't be too long, especially because we will be doing a lot of examples tomorrow. If you have anything you want to see done tomorrow, or another example of something, like say this example we just did was a little tricky for you, I'm happy to do another one. Just shoot me an email and let me know by the end of the day. Otherwise, this is all I have for today. If you have any questions, let me know, shoot me an email, or I'll stick around for a couple of minutes. But otherwise, I hope you'll have a wonderful Monday. I will send out your homeworks as soon as possible, and I will see you all for some practice with proofs tomorrow.